And I'm going to be talking about, of course, the latest ALTIUS limb instrument. Let's see if I can. There, good. So for the 5 or 6 of you in the audience that haven't seen this figure before, I should probably go through it. ALTIUS, of course, is, as people have just recently said, the orbit track is from left to right in this figure, and the limb instrument has 3 vertical slits shown there at the left, which are looking in the back along the orbit track. The center one is the only one that actually looks along the orbit track. We have, this is the 3rd ALTIUS to have launched. The second one, though, has no limb instrument, so this is the second limb instrument. And there will be 2 more after this. They're referred to right now as JPSS 3 and 4, but they get their names changed after, well, in this case, actually just before launch by NOAA. And the expectation now, I think, is that they're launching on 6-year intervals. So the last one should be still flying in 2040, we expect. The details of the spectrometer and the everything else are pretty much the same as on NPP. I won't go through those. So the launch was late last year, and we got our first light just over 3 months ago. The NOAA instruments are maintained orbits, so 1330 local time at equator crossing, and the NOAA 21 satellite is a quarter of an orbit behind the NPP one, so 25 minutes. These, what I'm showing here are the 3, for each of the instruments, the 3 orbit tracks of the tangent point. And so you can see that they actually are fairly close right now, but there's a big gap in between the 2 sets of instruments because it's only a quarter orbit, not a half orbit. In the future, they'll be half orbit apart for future missions. But what we get now is that we get crossing of the ground tracks, or the tangent point paths, up around 43 degrees north and 43 degrees south. So that offers an opportunity for cross comparison of the same scene, although 25 minutes apart. And as far as the lifetime of NPP, that's anybody's guess. It's up to NOAA. What we are been assured is that we're going to have 18 months of simultaneous operation between the 2, and at some point they're going to let the NPP orbit start to drift because they're out of fuel, or running out of fuel. But we hope that at that point they don't turn the instrument off. They just keep collecting the data, and we'll just have to deal with a drifting orbit. So just to show you some basic differences, there's a few small differences between the NPP instrument and the new NOAA 21 instrument. As I said, there's 3 slits. They're all imaged on a single focal plane, a single detector, and each slit has 2 entrance apertures. And what we've done is we've assigned a spectral range to each of the entrance apertures on NPP, and you can see that here. So for the east slit, what we call the small aperture has the vis and near IR, and the large aperture has the UV, and it's pretty much the same on NOAA 21. But what we did is, as we approached the NOAA 21 instrument, we said, well, we really want to improve the capability for aerosol measurements. So we did a number of things, one of which was to sacrifice one of the UV channels, since we really don't, for the upper altitude ozone measurements, we don't need 3 slits that are only 250 kilometers apart. So we sacrificed one of the slits to measure, to have a better measurement in the near IR. And we really haven't looked at that yet, but we're hoping that it has better stray light characteristics and a better sensitivity at higher altitudes. Another feature is that the NOAA 21 entrance slits are slightly higher. They're a tenth of a degree longer. So we do get an enhanced altitude range. But more importantly, one thing that if you look at the plot on the left here, you can see that, for reasons I won't go into, that the bottom of the slit, the tangent height, is actually always below the Earth's surface. So it's always viewing the ground, so to speak, and which is not very useful from a science perspective, but it's very good for bringing in unwanted stray light. So we were able to convince the satellite people and the rest of the instruments they should let us tip the satellite up a little bit. So we went up 10 arc minutes on NOAA 21 and were able to get it so that it's a bit higher in the atmosphere, which we think is helping a little bit with the stray light. It's not as much as if we go higher, but we couldn't sacrifice too much more of the lower altitude measurements. So the other difference is the timing of the measurements on the two instruments. Both instruments have, we cover the dynamic range, which is, 4 orders of magnitude, 5 orders of magnitude, from 0 to 60 kilometers, or 80 kilometers. We cover that with multiple integration times on the NPP instrument. It's just 2 integration times. So if you look at a plot of the signal noise as a function of height, you can see that when you switch from the short integration time to the long integration time, you get there's a big jump in the signal noise ratio. And there's also a lot of wasted time in that timing pattern that I'm showing on the top there. And so as a consequence, you're throwing away potential photons just because of the clocking of the CCD. And what we did on NOAA 21 is we came up with a much more efficient timing pattern, and it now has 7 individual integration times. And it's much more efficient at collecting photons, so we can see that the signal noise is actually better at the higher altitudes. And what that allowed us to do is decrease the repeat period from 18.5 to 15 seconds. So there's more images per orbit now. And when you're taking measurements simultaneously over that period, if everyone knows that just from basic geometry, that the tangent point, as you go higher in the altitude, moves closer to the observer. And so that's the effect I'm showing here, is that from every 50 kilometers, the effective latitude of the tangent point moves a degree. And so that's not particularly good when you're depending on altitude normalization to help correct for the direct outwelling radiation from the surface. And so what we did is we ordered the integration times almost like a scanning instrument, so that we measure the top of the atmosphere first, so with the long integration times, to the shorter integration times. And that gives us a much more stacked pattern of images, latitudes, which we really haven't evaluated yet how much it helps, but it can't hurt. Let's put it that way. Famous last words. One of the problems we had on NPP OMPS was there's a thermal sensitivity caused by the entrance baffle heating up when it's hit by the sunlight every orbit. And there's a thermal it actually deformed mechanically, and it put stress on these our mirrors, steering mirrors, the 6 steering mirrors. And so I almost think of it like you take your fingers and you push your eyeballs, and that's exactly what was happening. It was moving the image on the focal plane, and it caused both spatial and spectral shifts, because our detector is spatial in one dimension, spectral in the other. And you can see that in the plot up here, both spatial and spectral registration changed at that point in the orbit. On NOAA 21, the baffle mounting was redesigned. It was mounted in a different way to isolate it mechanically. So the expectation is it would help, and indeed what we see is on the left, this was the spectral registration as a function of time through the orbit. So this is a one orbit duration here, and we were getting several pixels shift in the spectral dimension through the orbit, and on NOAA 21 it appears to be much flatter. It's not totally flat, but it certainly looks like it worked. In the spatial dimension, again on the left, NPP on the right, NOAA 21, the same vertical scale, and there's a plot for each of the entrance apertures. So you can see the shift towards the end of the orbit, and that for the most part has been, it's improved, let's put it that way. However, when we go and we look at scene-based altitude registration, on NPP, we continue to, even after we corrected for the image shift, we continue to have this north to south or south to north variation in the tangent height of the scene, which is bad for ozone retrievals, to the tune of about 300 meters from 60 south to 60 north. And we were thinking, well, it's a different spacecraft. We're not going to have that on NOAA 21. Well, when we went and looked, we exactly got the 300 meter. Well, it's consistent with 300 meters from 60 south to 60 north. So we're starting to scratch our head now and thinking, well, maybe this is not a mechanical problem. This is actually a problem with our geolocation. So that's something we're going to have to look into. In terms of the absolute tangent height right now, when we evaluate what it was launched with, maybe I'm not sure if you can read the scale here, but right now we only have results for 2 of the 3 slits because we don't have the right wavelengths in the east slit. But what we looked at so far, 500 meters or 500 to 800 meters in the west slit, but over 2 kilometers in the center slit, which is really kind of a surprise. We didn't think it was going to be as bad as that, so we're not sure why. But again, we tend to use scene-based techniques to correct for these anyway. Moving on, like I said, we wanted to focus on improving aerosols, and that means stray light reduction. This is just a ground measurement of the scatter distribution, the point spread function from the primary mirror on NPP and NOAA 21, and also comparing that to the instrument internal scatter without the mirror. So there's somewhat of an improvement on the NOAA 21 mirror compared to NPP in terms of the scatter in the tails there. You can see we improved we changed the out of band filters, rejection filters, so that we're getting rid of any potential out of band stray light. Not all of it, but it should be a big improvement over NPP. We changed the coding on the actual CCD to optimize in the near. Oh, did I not do something?
Let's try to reforce it.
Did it have a timeout?
What?
Okay. So one of the classic problems with CCDs is because silicon starts to become transparent in the IR, you get this Etalon effect. You can see that in the NPP detector, and the coating helped reduce that, the anti-reflection coating. So we'll be evaluating that. There we go. And we did extend the Earthshine baffle, although you can see it's just a little bit extended. We couldn't go much further than that because it was starting to get in the field of view and other, of the nadir amps. Even the pre-launch test indicated that it wasn't going to help much. And as I mentioned before, we're now pointing a bit higher. We're not seeing as much of the ground, so that should help with stray light. So speaking of straight light, one of the tests we did post-launch is we do what we call the pitch-up measurement. The idea being that, so on the left here, you can see, oops, I got to restart. On the left, you can see this is a normal pointing for a measure. It's got my number.
So I don't know what's going on here.
So I have to get out of it again? Is that the way it works?
So we can get out of presentation mode
Just do it out of presentation mode.
and then again. But I think there is a, come on, voilà. And now we do that.
So then we pitched the satellite up by a degree, and we actually went more than a degree as well. The idea being that we eliminate a lot of the earth shine then, so that these...
And you have a pointer in the...
Yeah, but it doesn't work all that well.
Like on in your slide or something, it's like okay.
It's okay, all right, good. I'll do that then, it's a lot easier.
Actually, you don't touch.
Yeah, that's a good point, Donald. Thanks. So the idea being that this should not contain as much of the earth-shine straight light, and so these are the these measurements here are not corrected for straight light, and these over here are corrected for straight light. And if you look very carefully on the regular data at the high altitudes, there is a difference. Up around 100 kilometers, the correction does improve things. You can't really see any difference between those because there's so little straight light in the pitched up data. And the idea being that we can then compare how good our correction works. And so over here on the 508 nanometers, you can see that the uncorrected data that starts to tail up at the higher altitudes is an indication of straight light. But after the correction in blue, it stays fairly straight and agrees fairly well with the pitch up data. So it's a good confirmation that the straight light correction is working reasonably well. By the time you get to 869 nanometers, though, it looks like the assumption that the pitch up data is free of stray light is not really correct. You can see that even the red line there is tailing up. So and the point is that we have not yet corrected for the primary mirror scatter, which is, thank you, Donald. So we're hoping that once we get that correction tuned, that we can take care of that curvature at 869 and longer. These are some radio transfer model residuals that where we each one. This is for a matching orbit between NPP on the left and No 21 on the right. The top set is 350 nanometers. Bottom says 675 nanometers. Of course, at these wavelengths, there's no effective much gaseous absorption, so we're really dependent on the external information on temperature and pressure profiles, which we use MERA-2 for. There's some differences. The big difference here at 350 nanometers, you can see, and I'm showing a slice here at the on the right at the positions where they cross, the two orbits cross each other. What you've seen in blue, which is NOAA 21, that's the classic example of a tangent height error, which accounts for that. You also see that there's a lot of vertical structure in the blue. We've, since late last week, we figured out the problem there, and we've since corrected that, so I think a lot of that structure is going to go away. And then finally, these are some initial ozone comparisons. So each line in this plot is a different tangent height altitude, and it's with latitude on the bottom scale. And the solid lines are for NPP, and the dashed lines are for NOAA 21. You can see most of well, you probably can't see it, it's a little fine, but most of the NPP are, this is comparison with MLS, are near zero, within plus minus 5% in this particular case, but the NOAA 21 are still pretty far off, and a lot of that is caused by the tangent height. And again, these two slices here are for north and south, where the two tracks cross each other, and the green there you can see is running a bit low. So we've got some work to to do yet. I won't go through the differences again. I already discussed those. But some of the big errors remaining are the tangent height registration or the altitude registration. We've got to correct for the intraorbital, or maybe even find the root cause of the interorbital 300-meter change. And we've still got a lot of small radiometric problems to deal with, and we haven't even touched the seasonal variations. The spectral registration, we're assuming everything's constant right now. And we hope to release the level 1 data before the end of the year. I don't want to promise any sooner, but it'd be nice if you use it sooner. So thanks for your attention.